Welcome to the deep dive. So I think you've probably been there before.
Oh, definitely.
You get a transcription back from a long meeting, and it's just a total mess. The words might be there, but the speaker IDs are all over the
Right.
place.
Speaker one suddenly becomes speaker two halfway through.
Mm.
It makes the whole thing almost useless for, say, meeting analytics or any kind of legal discovery.
Exactly. And that's what we're digging into today. Speaker attributed time-stamped transcription, or SAS for short.
Essay test is the goal. It's not just what was said, but who said it and precisely when. The problem is the way we've traditionally done this is, well, it's a mess.
So tell us why that old setup fails so badly.
It all comes down to these brittle modular pipelines. You're basically, stitching separate tools together.
Okay, so you have one system for the words, the ASR.
Right. Automatic speech recognition.
Mm.
And then you bolt on a completely separate system for speaker diarization to figure out who's talking.
And that handoff between them is the main point of failure.
It's a huge weakness. Any error in that first step just cascades to the next. And, these systems have very limited context and, frankly, a fragile long-range memory for speakers.
So it's like trying to follow a play with short-term memory loss. It forgets who speaker one was after a scene change.
That's a great way to put it. And that brings us to our source material today, which introduces MOSS Transcribe Diarize.
A new model designed to fix this.
Exactly. It's a unified multimodal large language model, an MLLM, that moves to a completely end-to-end approach.
Okay, so if those brittle modular systems are the problem, how does MOSS actually get around these long-range context failures?
The core innovation is that it's unified. MOSS does everything: word recognition, speaker attribution, timestamp prediction, all in one single forward pass.
So it gets rid of those brittle handoffs completely.
It does. And the key to making it work for long audio is a massive 128K token context window.
A 128K context window is huge, so that means it can process something like 90 minutes of audio without ever chopping it up.
No chunking whatsoever. And that's why the quality is so much better. It preserves the continuity of the conversation,
So the model has the full context.
which prevents that speaker identity drift we were talking about. The output is just incredibly clean, structured segments, clear start and end times, stable speaker IDs. It even detects the language automatically.
That structural clarity is great, but let's talk performance. They tested this against some big commercial systems, right?
They did. GPT-4o, Gemini 3 Pro, 11 Labs. But before we get to the results, we have to understand how they measured success.
Okay, so we have CER, which is just character error rate, pure transcription accuracy.
Simple enough.
Yeah.
But the important one is CPCER.
CPCER.
It's a joint metric. It measures both the transcription and the speaker attribution together. So you get penalized if you have the right words, but assign them to the wrong person.
Ah, I see.
And the most important little nugget for you to track is something called delta CPI.
Okay, delta CPI, what's that?
It's just the difference between that joint CPCER and the simple CER. It isolates the performance drop that's caused only by speaker attribution errors.
So a lower value means you're much better at tracking who is speaking.
You got it. And MOSS consistently achieved the best performance overall.
But that smaller delta C is the real headline here, isn't it?
It really is. It's proof that having that global context just matters so much. MOSS delivered the lowest CER, CPCER, and delta C across all the benchmarks.
And these were diverse tests, long meetings, podcasts.
Even overlap-rich movie scenes, that tiny delta SP shows a level of speaker consistency that the other systems just couldn't match.
And we should probably mention, many of those big competitors couldn't even reliably process the long-form audio benchmarks.
Right. GPT-4o and Gemini 3 Pro, they basically failed on the long tests, which really underscores the gap in what's actually deployable right now.
So MOSS is really setting a new standard for reliable, high-context essay tests at a scale that's actually useful.
It finally unifies transcription and diarization into a single model with that massive context window.
This all raises a really interesting question for you, the listener, to mull over.
It does. So MOSS gets its edge from processing the full 90 minutes, that global context. But the paper mentions future work on streaming assets.
For real-time applications.
Exactly. So the question is, how might you design a system to get the benefits of that global context and stability while still adapting it for real-time, low-latency use? That gap between deep accuracy and instant delivery is the next big challenge.